Section 2 is over the first law of thermodynamics. And the first law of thermodynamics states that energy cannot be created or destroyed. So the energy of the universe is constant. The first law of thermodynamics is also called the law of conservation of energy, which we have looked at before. Which means then, okay, in our new terminology, that the energy that's lost by the system has to be gained by the surroundings. Alright, we're going to look at what we call internal energy. And internal energy is the sum of all the kinetic and potential energies of any component of the system. Okay, and the closed picture, the closed system in the picture at the right is the hydrogen and oxygen molecules. And you will see that picture on your handout. I just don't have it right here. Okay. The internal energy, okay, of that particular system, which is very similar to a slide from earlier, okay, includes all of the motion of the molecules, the vibration of the molecules, the rotation of the molecules, okay, and you don't know an actual value for energy, you just know how the energy changes. So you can never say, this is my energy. You gotta say, okay, this is how my energy changed. So again, you don't know the actual just energy value, we know the change in. You'll often see that as delta E. So now we're going to look at what exactly is delta E. Okay, delta E is when your system undergoes a change involving work being done or heat being transferred. Okay, you must have three qualities for delta E. You have to have the number, the unit, and the sign or the direction. Okay, because delta E is just like any other delta. Okay, it is your energy final minus your energy initial. So you need to have, what number is it? Is it 20? A unit, is it joules, calories, kilojoules, whatever? And the sign, is it positive, okay, or was it negative? Three things there. What does delta E indicate? Okay, if delta E is positive, that means that your energy final was greater than your energy initial, which means your system gained energy from your surroundings. Okay, if it is a negative delta E, that means your energy final was less than your energy initial, and that means that your system lost energy to your surroundings. So let's look at these pictures so that you have on your notes. Okay, if the energy of your system decreases, you lose it to the surroundings. The initial state is a higher energy than the final state, so it's negative. If your energy of your system increases, my initial state was less than the final, and energy was gained from the surroundings to get it to move up to be a higher energy. Right, in a chemical reaction, the initial state of your system refers to the reactants, and your final state refers to your products. And we have what's called an energy diagram down here on the right, and that describes the internal energy of the example. So, when we look here, okay, we have our H2 and our O2 to make H2O. Okay, that's the reaction we're looking at. So depending on which way you're going, will give you a negative energy or a positive energy. Okay, so if I take H2 plus O2 and make my H2O, and yes, I know it's not balanced, but it doesn't matter right now. Okay, that results in a negative number. So we're going this direction, downward. Okay, that's a negative delta E, which means that my system lost. If you're going the other direction, going from H2O to H2 to O2, which is up here, okay, that means I have a positive delta E, which means that my system gained. So it depends on which way you're looking at this, from which point of view, as to whether you are losing energy or gaining energy. And again, these are called energy diagrams. Alright, so let's get some practice here. It says the internal energy for Mg and Cl2 is greater than that of MgCl2. Sketch an energy diagram that relates this reaction. So I'm going to have Mg NCl2 is a higher energy, so higher energy is on top here. So the Mg plus the Cl2 is the higher energy. The MgCl2 is the lower energy. And I would just say if I'm going to go from this direction, my energy increases. So my internal energy is my y-axis. Okay. If I go from the Mg and the Cl2 to make MgCl2, my energy decreases. And that's how that looks. So let's relate delta E to heat and work. And the first thing is how we change delta E. Okay, delta E changes as heat is added or removed, or work is done by it or on it. If your system undergoes a physical or chemical change, you're going to either have positive or negative heat, and then either positive or negative work. And what we end up with here is that delta E depends on heat and work. Heat is a Q, lowercase, work is a W. So heat plus work gives you your change in energy. When you look at work done and heat added to a system, that should also have work done in the title. So we're either doing work or adding heat. Okay, that means that if heat is transferred to my system, that means that Q is positive. If work is done on the system by the surroundings, W is positive. And here's a little example off to the right. Okay, if heat gets put in, my system increases, is positive. If work is put in or done on it, then W is positive. So that means my delta E has to be positive. If we look at this table for Q, positive means it gains heat and negative means it loses heat. For W, positive means it's work done on the system and negative means it's work done by the system. Positive E is a net gain, negative E is a net loss. For this problem here, it looks a little long, but it's actually a very easy problem. We have two gases that are confined in a cylinder and piston arrangement, like in figure 5.3, which is a cylinder and then kind of a lid that can move. Okay. A and B react to form a solid product that is C. As the reaction occurs, the system loses 1,150 joules of heat. So my heat is Q. I lose, so it's negative 1,150 joules. To my surroundings, the piston moves downward as the gases react to form a solid. As the volume decreases under constant pressure, the surroundings do 480 joules of work on the system. So that's my work. It's done on the system. So that's positive. You're putting it into the system. What is a change in internal energy? Well, delta E is just these two added together. So we add the two together, negative 1,150 plus 480. We get negative 670 joules. Okay, endothermic and exothermic processes. We've done these before. This is nothing new. Okay, endothermic means it absorbs heat from the surroundings. These are where things feel cold. Okay, because the heat is passing from our hands to whatever container we have. Exothermic, that is the exact opposite. Exothermic will give off heat to your surroundings, which means you feel hot as the heat is leaving your system to the surroundings. Okay, the last thing we're going to look at is state function. This is something new. Okay, what is a state function? State functions are simply something that depends only on the initial and final state of the system, not on how it got there. So we're going to look at some kind of more normal examples of things that are state functions. Okay. If we look at the altitude difference between Denver and Chicago, it does not depend on whether you fly, drive, walk, crawl. Okay. Only on the elevation of the two cities above sea level. So an altitude difference is a state function. The distance traveled, however, though, depends on how you make the trip. Are you flying? Are you driving through Texas and then back up California and around? Where are you going? Okay, distance is not a state function, but altitude is. So we're going to look at internal energy and state functions. Okay, internal energies is a fixed value that is dependent on a set temperature, pressure, and amount. Alright, so I take, for example, the system here to the right. Okay, so I have a system of 50 grams of water at 25 degrees Celsius. all right, which is the one there in the middle hot plate. There are two ways that I could have gotten to this particular system. I could have either melted 50 grams to room temperature, okay, from ice, a solid, or I could have cooled it from steam. Either one of those two ways would have gotten me to that system that I have now. Okay, the internal energy at 25 degrees Celsius is the same no matter if I got it from cooling this amount or melting this amount. Doesn't matter, it's the same. Okay, so internal energy is a state function. It is fixed value. Doesn't matter how we got there, that's just what it is. Last thing, okay, when relating the internal energy equation. Because although delta E equals Q plus W, it does not depend on how the change occurs. The specific amounts of heat and work produced depend on the way that my change is carried out. So it's very close to my choice of travel route from Chicago to Denver. If you change the path by which a system goes from an initial state to a final state, it will increase by a value of Q. It will decrease that value of W by the same amount to kind of make up for it. So even though Q plus W gives you your internal energy, depending on how you got there, one will go up, the other will go down. And then you'll still have the same delta E.